Okay, great. Hi everyone. Welcome to the live discussion session. And I think we are in week 11 right now. I don't know. It should say week 11. Okay, never mind. So we are in week 11 right now. And this is the second last live discussion session that we'll be having for this semester. So it's safe to say we are at the tail end of the course. And we'll just quickly recap what we have covered so far. So this class won't go for the whole 2 hour. We can probably end it at 1 hour 30 or 1 hour 40 minutes, depending on how fast or how slow I go on. Okay. So if you recollect, till week 10, we had been looking at hierarchical RL frameworks. Okay. We have been looking at hierarchical RL frameworks. So what all we have covered so far? So in last lecture, we discussed the need for hierarchies in RL. That's the first question we addressed last week. Secondly, we discussed types of optimalities in hierarchical reinforcement learning. Okay. And we had started looking at hierarchical RL frameworks. Okay. So we had discussed there will be three types of hierarchical RL frameworks. First one being the options framework. Okay. Where we define macro actions for each subtask that we are supposed to solve. And the option can be defined by a three tuple based on the initiation state, the policy pi, and the policy for that particular option and the termination condition, right? And in the option framework, we looked at two kinds of Q learning methods. One was the SMDP Q learning, and the other was the intra-option Q learning. Okay, the options framework was covered completely in the last class. Secondly, we looked at the hierarchical abstract machines, or HAMS for short. In HAMS, we looked at how we can implement using SMDPQ learning for HAMS, right? We didn't really focus on the learning part as such for HAMS, but just a general idea of what this is all about. And this was also covered last week. One thing we didn't cover was the third framework, which is known as the max Q value decomposition, or rather the value function decomposition method. Okay, so in this class, we'll devote most of the time in looking at the max Q value decomposition function. This we did not cover last week. And I'll also cover some part of week 12 course content and most likely finish with the theory part of what this course has to offer. And next week, I want to exclusively devote to looking at the Python implementation on how one can design and solve RL problems. Okay, we'll look at pure implementation part. Okay, so this is what we had covered so far. So this is just a recap. Okay, so today we'll be looking at the max q value decomposition method algorithm. Okay, and we'll look at by uh, looking at the taxi world domain kind of a problem. Okay, before that, just to give you a intuition about what MaxQ framework is. So it's again a hierarchical reinforcement learning approach, which is designed to handle complex tasks, wherein we decompose the task into small subtasks, each subtask having its own reward function and the termination condition. So in such kind of frameworks, what happens is the tasks are defined in a hierarchical fashion. So we have a task, then you have a set of subtasks, each of which can be further decomposed into further subtasks and so on. So you essentially form some kind of a task graph, or you can think of it as a tree structure, right? So at each level of the hierarchy, what happens is you have two types of nodes. One is the primitive and the abstract node. So one kind of node, which is a primitive node, represents the actions that directly interact with the environment. Okay. And the abstract nodes are something that represents the subtasks. Okay. So we'll understand that thing in detail. So let me just go to the example problem. So let's say there is a problem known as the taxi world problem. Okay. How do I draw this? Okay. See, should I 1, 2, 3, 4? Okay. Yes. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So this is a 5x5 grid world kind of a problem. It's called the taxi world domain. Okay. I hope I'm still audible to you guys, and I hope everything is correct. Okay. So here, there are certain locations where the taxi can't go. So these are like the walls or obstacles. Okay. So it's defined like this. Okay. And there are four locations from where the passengers can be either picked up and dropped to. Okay. So the four locations are denoted by the letters G, R, B, and Y. So these represents the color of the pixel. Okay. So it's green, red, blue, and yellow. So these are the four locations where passengers can appear randomly. You have to go to that particular location, pick up the passenger, and drop it to the passenger's desired location. Okay. And you should do this more number of times to keep on accumulating reward. Okay. So the reward in this kind of a problem is defined uh, for each step that you take. So it's a grid world navigation. So the actions you take are either up, down, left, right in the grid world domain. So each step you take incurs a reward of -1. Every time you deliver a passenger to the correct location, you get a reward of +10. Okay. And if you pick up a passenger from a wrong location, let's say you go to a location where a passenger is not present and you perform the pickup operation. Okay. So that means you will incur a reward of -2. That means you're picking up a passenger where there is no passenger. Secondly, if you drop off a passenger at a location where the passenger doesn't want to go. Okay, so that also incurs a reward of -5. So that's more heavily penalized. So you have two kinds of actions here. One is the actions for the primitive level, which is the grid world navigation. And in addition, you have two abstract or subtask level action. So this is not a primitive level action. It's an action that represents the subtask. Okay. So similarly, we define the corresponding task graph for this problem. Okay. So what are the actions we have here? I'll just mention. So the actions are you go up, down, left, right. Then there is pick up, or maybe I shouldn't use up, down, left, right. Just to be consistent with what professor has here. North, south, east, west. Uh, North, south, east, west. Then there is pick up, and there is put down. Okay. So these are the entire action space. Okay. Here, these top four actions are known as the primitive actions. Why? Because these actions directly interact with the environment. And these actions are called abstract actions. Okay. Or you can say that these actions represents a certain subtask that can be decomposed into further smaller subtasks and so on. Okay. So if I were to define the hierarchy in this particular case, this is the action space, right? So if I were to define the hierarchy, so or the task graph, okay, this is how it would look. So in the beginning, you have a root node. Okay, this is where the main control of the MDP remains. The main control is that pick up passengers and drop to the desired location. The root node is decomposed into two subtasks. What could be the two subtasks? One is the subtask saying pick up, okay, and the second subtask is drop off. So if you have no passengers, you perform the operation of pick up passenger. If there are passengers present, you perform the operation of drop off. Okay, that is there. So there is okay, I'll come to that later. So now this pickup subtask can further be decomposed into more subtasks, right? One of them is, so if you are performing the subtask of pickup, so you actually go and pick up the passenger. Okay, so this is a action, primitive action, right? So maybe I incorrectly said this. All of these are primitive actions in this case. Okay, so these so if I indicate this by a double line, that represents it's a primitive action. Or when you are doing the pickup subtask, the second thing that you can do is you can navigate, right? You can navigate. Okay. Similarly, for drop off, you have the same. You can either navigate or you can perform the put down operation. Okay. So by put down, what do you mean? That the passenger has reached the location and the passenger gets down. So it's again a primitive action denoted by this sign. Note that navigation in itself is not a complete subtask because you need to pass an argument, navigate to a particular location. So a passenger gives navigate to location G. So that argument needs to be present in the navigate subtask. And similarly, if you finally decompose the navigation subtask, you are left with the four primitive actions, right? What are the four actions? You have north, you have south, east, and west. Okay, and these are your primitive actions denoted by the double dash lines. Okay. Yeah. So these lines are known as the primitive actions. Others are the non-primitive actions. So the idea is simple. You have defined a hierarchy of the different subtasks or subroutines that the algorithm needs to do. So there's a main task, which is a root task that makes a call to the lower subroutine or a lower subtask, which performs something simpler, which is say the pickup and the drop off operation. Even further down the hierarchy, you look at the navigation operation, the operation to yeah, perform the pickup and the put down task and so on. Okay, so all these things are included in this task graph itself. So it's a nice hierarchical framework wherein things can be designed. Note here that there is no notion of a sequentiality, right? Reason being, so if I am performing pickup, so I need to first navigate and then pick up, right? I can't do pickup and navigate. That also can be done, but that notion is not represented in the task graph that is present over here. So if pickup operation, pickup subtask is invoked, I first have to navigate to that particular location and then perform pickup. If the drop off subtask is invoked, then first I have to navigate to that particular subtask and do perform the put down operation, right? So that notion is sort of abstracted in the formulation. Okay, and note that this particular framework or this particular formulation needs to be a directed acyclic graph, and this is a necessary condition because you don't want a loop to be present, right? So it's necessarily a DAG or a DAG. This condition needs to be satisfied necessarily. Otherwise, you can simply uh, get stuck in a particular kind of a loop. So this kind of a hierarchical framework is the first step in designing the MaxQ architecture. Okay, or the MaxQ framework. I should use the word architecture. Just a sec. Okay. So, in this case, the key idea is simple. Okay, so key idea behind the MaxQ framework is that we use a different value function for each of the subtasks in the hierarchy that we are trying to perform, right? So this sort of enables the learning algorithm to focus on learning the subtasks that are the most relevant to the overall task, okay, rather than it trying to learn everything at once. So such kind of a division or dichotomy is present in the MaxQ framework. Okay. Also, as we'll see, the MaxQ framework introduced a new type of Q value, which is known as the MaxQ Q value. Okay. So what it does is it represents the expected return from a given subtask while taking into account all the subtasks that has to be completed before the particular subtask is being executed. And the good thing about it is it can be decomposed recursively into smaller subtask values and thus allowing for efficient learning of the hierarchy present in the model. Okay. So I have so a lot of things. So to put it down mathematically, first we say that M is the MDP or set of tasks that needs to be done that is decomposed into M1, M2 dot MK. So it's decomposed into K subtasks. Okay. Where each subtask, the ith subtask contains the variable of the state. Okay. Then there is the action. Then there is the something known as RI bar. Okay. So the state consists of what? The state consists of uh, where the location of the taxi is present, right? So if I say SI, so what SI consists of is it contains the location of taxi, right? So the taxi can be present at any of the 25 locations, so 5 cross 5 grid. So any of the 25 locations minus the 8 obstacles. Okay, so let's say the taxi can be present in any of the 18 locations. Is it 18 or 17? I think it's 17. So the taxi can be present in any of the 17 locations. Second is where the passenger can be. Okay. So passengers have to be necessarily initialized at any of the 4 locations, which is V, R, B, Y. Plus, the passenger can be sitting inside the taxi. Okay. So if I were to take the location of passengers So in total, I have five such locations. Okay, and finally, I need to have the location of the destination because that is also important, right? The location of destination. So this is four because I have four destinations that I can go to. Okay, so this entire thing consists of state space, which is 17 cross 5 cross 4. So these are the total number of accessible states that is available to us. Okay, this Ri bar function is known as pseudo reward. So this can be thought of as the reward that the agent gets on completing the ith subtask. Okay, so you can think of it as a reward associated with subtask. So there is a core MDP reward that the core MDP handles, which is completion of the main task at hand. And secondly, there is the pseudo reward, which gives a reward for completing a particular subtask that is present. Okay. And along with that, you have some set of terminal states. Okay, so basically a subtask is invoked if it is not present in the terminal state. Okay, meaning if I am currently at any of the terminal states where the subtask terminates, then the subtask doesn't get invoked. Okay, so you can think of it like this. So if Ti is the set of terminal tasks, then Si is the state of accessible task, which is non-terminal. So this constitutes the entire state space. Meaning that if I'm in the terminal state itself, then that subtask never gets invoked. Okay, that's there. And secondly, you can think of each subtask as a collection of semi-Markov decision processes, right? Or it's a collection of SMDPs. Okay, so what we do is, so if I define the SMDP part, so the ith subtask can be represented by the states Si, actions Ai. Next up, we have the transition probability for an SMDP, right? So this is Pi. You have S prime tau. Tau is the number of time steps required to execute that particular subtask or the sub action, right? Given my state and action, okay? And similarly, you have the associated reward function. So you have Ri, which is S, A, S prime, and tau. Okay, so this constitutes the entire SMDP for a given subtask. Okay, note here the reward function, which is RISAS prime tau, is essentially what? It is nothing but the expected reward RT plus gamma, RT plus fun, dot, and so on. Given that my ST is SI, my AT is AI, and that I'm following a policy pi. Okay. So this is the reward that you get from the core MDP side of a thing. Okay. And secondly, you have the pseudo reward component, right? Which is the reward on completion of a given subtask. Okay. Now we will try to actually assign value functions to this kind of the max-q value function decomposition method. But for when we are defining the value function, we'll kind of neglect the Ri hard bar term. So we'll ignore the pseudo reward component in this case. Okay. The reason being that it makes our life easier for now. Okay. So once you introduce that, then that's a different formulation in itself. We won't go into that right now. Okay. So to define a value function, first of all, I need to know the value function of the state S. Okay. This is for a normal MDP problem that we try to solve typically in the reinforcement learning setup. Here, we denote something called as v pi I comma s. Okay, so this is in short a projected value function. Okay, so when I say it's a projected value function, what I mean is, so this is the value that, or this is the expected return that you will get on completing the subtask I starting from status. Okay, so in a way you're projecting it out into smaller subtasks, hence the name projected value function. But v pi I of s denotes the expected return on the completion of subtask I starting from status. Okay. Now, if we have defined this, we can define the Bellman equation for this value function as, so I have v pi I comma s is r of pi I of s. It's like basically I'm taking the first action at status, okay, which I'll denote as pi I. So when I say I'm taking the first action, that means I'm making a first call to the smaller subroutine. Okay. So it need not necessarily always be a primitive action. It could also invoke another subtask if we think of it from the task graph notation, right? Plus, you have the Bellman component, which is the summation over S prime tau. Note that we are not summing over actions because we are dealing with deterministic policies. Okay, so this is Pi of S bar tau given S comma pi I of S. Okay, that's why there is no summation over actions in this case. Okay, times gamma tau of not R but rather V pi I comma S prime. Okay, so this is the Bellman update rule for the projected value function. Notice, if I just copy this line, so if this is clear, notice that what is R of pi I given us, which is the reward that I get on executing the action at status, which is the initial state that I have. Okay, so that can also be defined as the as a value function, right? If I were to define this, which is the reward that I'm expected to get starting from status, and I take action pi I of s. Okay, so this is denoted by, this is denoted by what? This is denoted by the value function when I'm executing the pi ith subtask starting from status. Okay, so this is what this reward function can be denoted as, right? Just move it a bit here. Okay, so this is the Bellman equation for the uh, state value function methods for the state value function. Okay, similarly, if I were to define the q pi, uh, if I were to define the q function, okay, so what it would look like, it is, sorry, it is, let's see, q pi for executing the ith subtask given state s and action a. Okay, so this is nothing but the original v pi. Instead of pi I of s, I have the action which is given to me, right? Meaning the value function for the AH subtask, okay, starting from status, and rest remains the same, right? So it's like the value, the expected value function on executing the first action, which is A, and after that I follow policy pi. Okay, this is going by the standard definition of the Q function. So I have S comma pi I of s, we have gamma tau v pi I comma s prime. Okay. Now, we represent this as the following. Okay. You can also write this as v pi of a comma s plus, we call this additional term over here as c pi of I comma s comma a. Okay. So this is the entire second term. So this is also known as the completion function. So now my q pi of s is basically the sum of the value function that I get on executing action A or the Ath subtask at state S, then the completion reward that I will get once I complete uh, the subtask, once I complete the ith subtask, starting from state S and taking action A initially. Okay. So that's the reward I get for completing the particular subtask. So this is how the definition looks like. And here my, okay, so my q pi I s comma a is my b pi a comma s plus c pi of I comma s comma a. Here my v pi a given s is simply uh, q pi of a comma s comma pi I of s, or rather pi a of s. Okay. If a is non-primitive. Okay, if it's a non-primitive action, then I make a further call to the lower uh, subtask, the lower at hierarchy subtask, and I invoke or I look at the queue function for the subtask at the for the eighth subtask in this case. Okay, if that is not the primitive action. Okay, if it's a primitive action, then I simply give the termination reward condition, which is s prime. So you have p of s prime given s comma a. I should try to make it neat. So I have p of s prime given s comma a times the expectation of reward for the SAS prime combo. Okay, and this is applicable if A is a primitive action. Should write action also here. Okay, so this is how the value function method goes. So in a way, you can think of it as, okay, so with this definition, we can start by defining the value function, okay, for the core MDP. So for the core MDP, okay, for the 0th subtask, okay. So the value function for the 0th subtask is simply the completion function for 0s a a1 plus v pi of a1 comma s. Okay, so assuming I'm following policy pi, okay, and let's say my pi 1 of s, or the first action according to the policy, is a1. Okay, so if I do that, then I first so I have written it, just flip the location here. Okay, so first I write the completion function. In a moment I'll tell why. So I get the reward for completing the 0th subtask starting from the first action A1, and second is the value function for invoking the A1th subtask. Okay. So once I invoke that also, so since my A1th subtask is not a primitive action, so that can also be recursively written as the queue function, right? So this is C pi of OSA1, which was present, plus since this is a non-primitive action, we again look at the associated queue function for this, okay, which is again the completion function for the A1 of subtask where I'm at S2 and I start with action A2 plus the associated value function for the A2 at subtask, okay, and so on. Okay, so you can extend this further ahead. So this becomes, sorry, this becomes C pi A2 comma S comma A3 plus my V pi of the A3 at subtask and so on. Okay, so in a way, what you're doing is you're doing a breakdown. Okay, you're doing the breakdown of the value function into smaller chunks. Okay, think of it as smaller chunks of value functions. So you have a big value function for the core MDP based on the hierarchy that you have prepared from the MaxQ framework. You have separated the value functions into small chunks. Okay, based on the completion function method. And the good thing about this is that we can reuse the completion function, okay, which is a good thing for us. So if a particular subtask is getting invoked quite often when we are trying to solve an MDP, like for the case of pickup and drop, the navigation subtask gets invoked more frequently than other subtasks. Okay, since the smaller domain, so navigate has uh, gets invoked more number of times. So if we try to learn the value function based on the completion function that is available to us or that is present, so more number of occurrence of that means that we can simply reuse the completion function. We need not compute it again and again. So this is the advantage. Okay, so we already have the value function. We can directly use that. So that reusability factor comes in. Okay, secondly, we can, okay, secondly, we can reuse few functions. Okay, this goes here. Okay, so this is the advantage that this value function decomposition method offers. Okay, so overall, what this MaxQ framework did is this MaxQ value decomposition method helped me in providing some kind of a structure or an efficient approach to solving the hierarchical reinforcement learning problem. What we did is we started with a big task, we break it down into smaller subtasks, and then using the MaxQ value decomposition method based on the maths that I have defined so far, uh, we compute the value function of the abstract subtask that we have. Okay, so we did not only deal with the subtask of the core MDP, but we are dealing with the uh, value functions of the smaller subtask. Okay, so MaxQ offers a neat method to do such kind of operations. Okay, so with this we complete the three hierarchical framework methods. Nextly, we'll quickly look at the option discovery part. Okay. So we look at the option discovery part. So options are typically easier, neater, and widely popular, right? For many use cases of hierarchical reinforcement learning. So what happens is the idea here is whenever we are typically trying to use option framework, we need to define good options. Okay, so we need to say what is a good option and how that option can be beneficial to us. So there are certain criteria that defines a good option in this case. Okay, first is sorry. So the first criteria that a good option must satisfy is that should be reusable. Okay, reusability. Reusability. This is the first condition that a good option needs to satisfy. Okay. Second is it should cut down on exploration, right? This is also a property that a good option needs to satisfy. And thirdly, it should help in transfer learning. Okay. So heuristically speaking, these are the three methods that these are the three indicators for a good option, and we want to basically try and discover good options more often. Okay, so turns out since there are no algorithmic or deterministic method to look to define a good option, so we typically rely on surrogate measures, right, to discover good options. Okay, one of this kind of thing is known as bottlenecks. Okay, so one of these kind of methods is known as bottlenecks. So what we mean by a bottleneck, it means that from going from one state to the other, you need to pass more often through some state, which is like kind of like an access to another state, right? So if you recollect the door example, okay, so I have two rooms, okay. To go from room one to room two, I have two doors. Okay, this we had seen last week also. So this is room one and this is room two. So typically these doors are good bottlenecks, right? So if I want to go from uh, this left half of the MDP to the right half of the MDP, I need to pass through this bottleneck points, okay, or these can also be known as the access states. Okay, I need to pass through such access states to go from this location to this location. Okay, so this typically denote the bottleneck in this refers to the bottlenecks. Okay, so turns out having a bottleneck state is a good option. Okay, so a bottleneck can be a good representation for an option. Okay, so the more we reach to a bottleneck state, the better is our chances for uh, a successful completion of an episode. Okay, so how do we discover such bottlenecks? Okay, so one way to look at it is, so it turns out there are a few methods to discover bottlenecks. So we quickly mention methods to bottlenecks. Okay, so one method is graph partitioning. So what happens in graph partitioning is you take the entire state, entire MDP, and try to represent it in a graph structure. Okay, and then if you draw all the connections from each state, what all states you can go. If you represent it in terms of graphs, you will see that there are certain nodes that might be very weakly connected. So if you want to go from the left part of the graph to the right part of the graph, you need to pass through those states, and those states are usually weakly connected. Okay, so these kind of states through graph partitioning represents a bottleneck. Okay, so this is one method to find out the bottleneck states. Second method is known as diverse density method. So what happens in diverse density is you have the MDP, you start drawing random simulation samples. Okay, so you recollect the idea of using an experience replay buffer. So you sample lot of trajectories, and then you actually maintain the trajectories. You look at the history of the trajectories and see. Uh, so you have a bunch of trajectories that were successful. You have a bunch of trajectories that were unsuccessful. So you see the occurrence of a particular state in the successful trajectories would be disproportionately more than the occurrence of other states in the unsuccessful trajectories. Okay, so this is a good indicator of a bottleneck. You have so if you were to pass through the door neck for a successful trajectories, the state which is passing through the door neck, passing through the doorway needs to be present in the trajectory. Afterwards, it might fail. Okay, once it enters room two, it may be possible it didn't reach the goal, but the presence of these bottleneck states in the uh, successful trajectories would be disproportionately larger than the failure cases. Okay, so this is another method, the diverse density method, to discover good options. Okay. Secondly, you have some. So thirdly, you have something known as betweenness centrality. So this is a metric which is fairly popular if you have studied courses on network theory or network analysis. So betweenness is basically a measure. It basically computes the number of shortest path that passes through a node. Okay. So if I were to go from a start to goal location, so the number of shortest path that passes through a particular node is defined as the betweenness centrality for that particular node. So turns out higher betweenness centrality necessarily denotes a bottleneck. Okay, so there are other methods also. There is node centrality, there is degree centrality, but these need not necessarily denote a bottleneck. But betweenness centrality is a known method to detect a bottleneck in a graph. Okay. And lastly, you have something known as small world options. So it's like you break down the big world you have into small walls, into into small worlds. Okay, and based on the small world, you define some option which takes you from one particular world to the other world, and this necessarily could be an indicator of a good bottleneck. Okay, so breaking down into small world options can also help in determining or detecting a good option or the corresponding bottleneck states. Okay, so with this we cover entirely what professor had to cover in the hierarchical reinforcement learning section pertaining to this course. Okay, the content are still vast. Okay, people are actively doing research in the planning and the RL community related to hierarchical reinforcement learning. So this was just a slight introduction to the different hierarchical RL frameworks which are present. Okay, I'll go to week 12 section now. It's already 7. Maybe I'll take class for another half an hour. Then we can close it. Or maybe we go till 7:40, right? Because we started at 6:10. Let's see. Where was I? Yes. So we look at something known as partially observable Markov decision process. Or POMDP for short. Okay. So POMDP or partially observable MDP is typically an extension to the Markov decision process. So we have seen the semi-Markov decision process, okay, where we had durative actions. Here we don't have durative actions. We have the actions similar to the MDP, but the states are different, okay. So while an MDP assumes that the agent has access to the full state of the environment, a POMDP assumes that the agent only has some partial or noisy observations for the environment. Okay, it doesn't have the global access to the environment, but some kind of partial or noisy observation. And in a POMDP, the state of the environment is not directly observable by the agent. Okay, but rather the agent receives or it perceives certain observations that are mostly noisy and incomplete, and the agent uses that particular observation to make decisions. Okay, so you can think of it as in a real world example. So let's say you go to a doctor, right? So and you start describing the ailments that you might have. So you describe, okay, you have fever, uh, you have high BP, you have low sugar, and all descriptions or a certain test that the doctor performs using his or her equipment. And based on that, what the doctor perceives, what the doctor sees, the doctor cannot directly determine the disease or the ailment that the person is having, but rather it makes use of the observation that are present or that information that the patient gives. And based on that, it makes a decision or it makes some prediction on the state or the ailment or the disease that the person is facing. Okay, so this is a real world example of a POMDP. Okay, typically, whenever you have an agent, so consider another example for robot navigation, right? So one thing is the robot has a GPS sensor. So it has the complete idea of its current XY position along with uh, the idea of the obstacles, where the goal is, where the start is. Okay, so this is a full information. Secondly, there is another kind of navigation wherein the agents don't have a GPS. There is no means for localization, but they rely only on their sensory information. So if they have a camera sensor, if they have a LiDAR sensor, based on that, they make observations. They detect, okay, these are the obstacles, and based on that, they make a prediction. Okay, I could be in this particular state. I could be in that particular state. Okay, so it's kind of an observation that the agent is making. Okay, so turns out that okay, so first I should draw this table. So, so if I were to define the Markov models, okay, so there are four ways I can categorize it. Okay, firstly, do we have control over the state transition? Okay, and the answers could be either it's no or it's a yes. Okay, you either have access to the control over how you transition, and second is are states completely observable? Okay, this is the second question. Maybe this should be shifted a bit. Okay, into this question, also there are two answers. You say either yes or no. Okay, I hope I'm still audible. I'm still visible. Okay, great. Yeah. So if a state is completely observable, but you don't have control over the state transition, it's simply a Markov chain, right? But if you have control over the transition state, it's called an MDP. It's a Markov decision process. If states are completely not completely observable, but you also don't have control over the state transition, so it's a hidden Markov model. Okay, or what you call as HMMs. But if you have control over state transitions and the states are not completely observable, then this is known as a POMDP, right? It turns out there are certain advantages, right, for using MDP between an MDP and a POMDP, right? So for an MDP, first is an MDP is tractable to solve. Okay, one major advantage that an MDP provides. Secondly, they are relatively easy to solve because there are no complications. You have the entire state action transition probability and the reward function defined. So these two are the advantages for an MDP, wherein the drawback is that it assumes perfect state knowledge. Okay, okay. Secondly, look at POMDP. So in POMDP, you say that it treats all sources of uncertainties uniformly. Okay, so there could be two types of uncertainties. First is the uncertainty due to the noisiness in the sensor observation. Okay, that is one type of uncertainty. Second is the uncertainty in the action execution. Okay, if the environment is slippery, you intend to go left, but because the environment is kind of slippery, or if there is a wind blowing, you go with some probability, you go to the right. That is also possible. So there is an action uncertainty. So in POMDP, all sources of uncertainties are treated uniformly. Okay. Secondly, it allows for information gathering actions. We'll see in a moment how. Okay. But the disadvantage is hugely intractable to solve optimally. Means you can solve for a POMDP, but it's very difficult to find an optimal solution for a POMDP model. Okay. So look at the example that professor had covered in class. So assume you have a partially observable model, okay, where the environment is defined as follows. So you have like a figure eight kind of a structure, okay. So the agent can move around in the figure eight structure, and let's say this is a grid world, okay. So I just say this is the different grids, okay. This is the grid. Oh, no, I mean, again, let's start again. So you have this figure eight kind of a thing, okay. And along with that, you have This one, right? Yeah. They are small uh, grids. Okay. I'll just take a moment to draw this. Okay. So this is the different grids are available, and the agents don't observe the current cell that they are in, but they only make an observation of the world around them. So, like, so if the agent is here, the agent can sense the four obstacles in the four directions: north, south, east, west. Okay. So, and the ordering is in this fashion. Okay. So, if there are no obstacles, you define it as 0, 0, 0, 0. If there is obstacle on the north, so it's north and then 0, 0, 0. No obstacles on other side and so on. Okay. So, this is how you define the states or rather I should use the word observation now for the agent. Okay. So if I were to look at it, so what are the possible observations that the agent receives in this particular world? Okay. So let's list it down. So I have 0001. Okay. Meaning there is obstacle on the west side. Okay. Obstacle on the west. Only obstacle on the west. Three side there is no obstacle. Which location is this in here? I think it's this particular location, right? So this occurs once. Okay. Similarly, you have 1010. This occurs at six places. Right. North south obstacle is there. Secondly, you have 0101. That means obstacle is there on the east west. This occurs eight places. Then you have 1100, which is one. There is 0110, which is one. Okay, only one location. Then there is 0011 and 0100. Okay. So these are the available information or the available observations that an agent receives. And based on this observation, the agent has to decide which state I'm actually in. Okay. So let's say, firstly, the agent observes the state 0101, meaning there are obstacles on the east west, no obstacle on the north south. So if I look here, I could be at five different places. Okay. One is I can either be here or here, 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 here. Okay. So that means I could be at a location with any of the location with probability 1 by 8. Okay. Based on this observation that I have. Now let's say that the agent takes an action. The action is to go north. Yeah. The action is to go north. Okay. And after going north, the agent again observes this same thing that in like east-west obstacles, north-south obstacle free. Now, based on this information, we know exactly, we don't know exactly, but we can say for sure where the agents could be, right? So, where is the eraser? Okay, here. What is this? No, no. Let it be here for now. I shouldn't touch anything. Okay. So, based on this information, we now have four places that the agent could be, right? Based on the history. So, if I was at 0101, I observed 0101. I went north. I again observe 0101. Okay, let's say I again move to here. I again move north, and now I observe 1001, meaning there is obstacle on the north and on the west side, but no obstacle on the south and the east side. Meaning I can exactly say, right, I am at this particular location based on the history that I've observed so far. So, so now I know with good probability I can say uh, that I am at this particular location. So what this small exercise did is based on the observations that the agent get, immediately there might be a high probability, like a lot more uncertainty about where I could be. But the more amount of steps I take, or the more history that I undertake, I uh, I basically determine where I can basically pinpoint the exact agent location. So in a way, the more steps that I take based on the current belief I have. Okay, so I introduce something known as a belief state. Before that, maybe I should say that. So this kind of sequence is a uniquely identifying sequence, right? It's a uniquely identifying sequence. And what we are doing is we are tackling partial observability using history. Fine. Here, let's say initially I have some probability distribution. So if the probability I am at state as uh, given observation 0101 is 1 by 8. Okay. After this sequence, now my next probability becomes 1 by 4. Okay, because I have removed certain part. But after that, if I see another sequence, I can say with probability 1 that I am at this particular location. Okay, because it's a uniquely identifying sequence. And based on the history, I can also know that the way the agent could have started to reach there. Okay. So this kind of things are known as a belief state. Belief states. Okay. This was a small introduction to the notion of belief states. So what is a belief state? Okay. So a belief state is basically a probability distribution over world states. Okay. You can say that my belief of S is the distribution over the world state. Okay. Here, my action update rule is, so if I take anytime I take an action, so my action update rule is, so for A fixed, okay, I say that my belief of S is simply the summation over all S prime that I could go to probability of S prime given A comma S into the previous belief that I had over state S. Okay. So based on that, I update my belief for S prime. So I should change this here slightly. Okay. This is the action update rule. And similarly, the observation update rule is, My bell of S is simply, or I should write it here, my bell of S is simply probability of observing O starting from state S times the belief of S that I had. Okay. So this is the observation update rule. So this gets dragged here. Fine. So this is the definition for belief state. What else? What else? Yeah, small example before that. So let's say this is also the one of the question in the practice assignment or the practice quiz. Okay, in week 12, I'll solve just one example. Now imagine you have a 3x3 grid world. Okay, where this is an obstacle. And let's say the agent is at position X. Okay, here we say that the sensory or the sensor accuracy, or rather the correctness, is 0.9. That means a sensor can sense an obstacle with 90% probability. It gives wrong result with 0.1% probability. Okay. Now, the question here is, given that my sensors detect there are no obstacles, everywhere there are no obstacles, what is the probability I am at the location marked by X? Okay, this is the question. So to solve that, we say that P of X given my observation is 0, 0, 0, 0. Okay, we'll simply apply the rules for conditional probability. We say that this is P of X intersection of 0, 0, 0, 0 divided by the probability of getting observation 0, 0, 0, 0. Okay. Now the probability of me getting being at location X and getting observation 0, 0, 0, meaning that at this particular position I can be at that particular position with 1 by 5 probability at the position marked by X, and the probability that all my sensors give 0, meaning that all my sensors should fire correctly, which is by a probability of 0.9 by 4. So each direction my sensors should tell me with correctly that there is an obstacle or there are no obstacles, or if there is an obstacle present or not. So in our case, if it is 0, 0, 0, 0, that means it's 0.9 power 4 probability divided by what is the probability that we get the reading 0, 0, 0, 0. Okay, one is I am present at the location marked X and all my sensors fire correctly. This is one option. Or secondarily, I can be present at the remaining 4 by 5 position where two sensors fire correctly, but two sensors misfire. That means they give wrong result. Okay, that is also a probability of me getting the observation 0, 0, 0, 0. So this is how you compute the probability. Okay, so what do you do? How do you compute? So let's say I did cut 5 everywhere and zero point 0.9 square gets divided throughout. So I have zero point 0.9 the whole square divided by zero point 0.9 the whole square plus zero point 0.1 the 4 times zero point 0.1 the whole square, right? So this is 0.81 divided by 0.81 plus 0.04, right? Or did I miss something? Yeah, actually, I made a mistake here. So at the remaining three positions, I want three of my sensors to misfire. One sensor will give the correct reading. I want three sensors to misfire. So one gives correctly, but three sensors to misfire. Okay, there's a slight change here. And you can see why, because I had considered that everything out of it is a non-obstacle, but it is in fact an obstacle. Something here, here is an obstacle. This the sensor should detect. So if I am at this particular position, there are three obstacles and one non-obstacle. So three sensors should misfire, right? So now, how does my equation look? So it's zero point 0.9 the whole cube now divided by zero point 0.9 the whole cube plus 4 times zero point 0.1 the whole cube. Okay. So now let's start looking at it. So it's 0.729 divided by sorry, 0.729 divided by 0.729 plus I think 0.004 if I write it correctly. Okay, I am not sure. Maybe computation you can do, but I can tell the answer is 82 by 91. Okay. So you understand the method how to do it. You can do the calculation later on. So there are two questions. I have done one of it. Second question says that if obstacles are present at the north and the west, like if my sensor detects that my reading is 1010, what is the probability that I'm not at the location marked by X? Okay. So what you do is you compute the probability of X given 1010 and you do 1 minus probability of X given 1010. That's the way we usually solve such kind of problems, right? So we'll quickly look at two methods for solving POM DPs. Okay, this is the last part. So solving POM DPs. Uh, so professor had mentioned two methods to in class. He had mentioned four methods, but he has discussed two methods. I'll discuss those two methods quickly, and then we can call it a day. First is something known as a history-based method. Okay, so what do you do in a history-based method? You start by maintaining the history of all the states that have been observed so far. Okay, so let's say initially you observed 0101. Okay, okay, second, okay, in the second time step, let's say now your state become uh 0101 again. Okay, third time step it becomes 0101, 0101, comma, and there's a comma of 1001. Okay. This is something that we had seen in the previous example as well. So you typically start by maintaining a history over these states, and then you operate the Q function, right? So let's say you operate the Q function over this, and let's say the actions that you take, you also mention that here. Okay. So the reason we do that is saying that we took action when we had the state 0101 twice could refer to a lot of uncertainties. Like it could say that I went up, then my sensors misfired, then I went up, but I got this reading or something like that. or if I went down, then I went up, but both times my sensors misfired, so I got this reading. Okay, so introducing the actions that have been taken in the history itself tries to disambiguate uh, that particular inaccuracies or uncertainty that one could face in such kind of methods. Okay, so you typically work with histories to solve the different POMDPs which are available. Okay, so there are some drawbacks for this kind of methods. First is you have large state spaces because you are maintaining a lot of history, right? So you have a large state space. Second is all your state space have unequal description. Okay, so the first state will be smaller, the second, third states will be disproportionately bigger, and so on. So you have unequal state description. And thirdly, there is wastage of computation. So you are again and again computing, like storing the same state value in consecutive steps. So a lot of resources and computation gets wasted in this particular case. Okay. Second case is known as it's like a QMDP like model. Okay. So typically you do one thing from the POMDP that you have which available, you solve the MDP portion of it. So assuming you have the POMDP given to us, which is made available to the agent. So you solve the MDP component first in the POMDP. Oh, by the way, before that, did I define the POMDP? No, right? Okay, okay. Just a sec. Sorry. I should define it quickly here. So a POMDP is defined by the states, actions, the probability transitions, rewards, which is present in the MDP component as well. Uh, in addition, we have the omega parameter, which is the set of all the possible observations. So in this case, if it is 1, 0, so for the 4 wall reading that we have, so it is 0, 1, the whole power 4. It's the power set of all the possible observations that the agent can get. Lastly, you have the observation function. So this observation function basically maps from the observation to the state. So it can be defined as it maps from the state action and the observation that you have, and it gives a probabilistic output, basically saying that given the state and the action that I have taken, and if I have observed this, what is the probability that I am at this particular state? Okay, so this gives you a probabilistic output. So I forgot to mention that. And so you solve the MBDP component. This can be done easily, but the execution is still a problem, right? Because you can't, if you once you solve the MDP, you start by executing the it like an MDP fashion, but what you're typically dealing with is a POMDP, right? So execution still a problem. So what you do typically in this case is you uh, store the belief. Okay, so you say whatever belief you have, you multiply it with the Q function that you have solved from the MDP component that you have, and then you sum it over all the beliefs. Okay, you make a summation over all the states, and you say that this is called the Q bel of S comma A. Okay, so this is how you do it. So you solve the MDP component, take the belief of all the possible states that you have, you multiply it with the Q function that you have, and then you term it as Q bel of S comma A. And finally, the optimal policy here can simply be recovered by taking the argmax over the Q bel S comma A. Okay, this is one more method to solve the POMDP problem. Okay. Third and fourth, professor mentioned about directly solving the POMDP. Okay, therein he says that first is that you have an approach where you assume the model, and secondly, you deal with a Bayesian approach. Since he didn't go into detail, I also skipped this part. Uh, Lastly, he mentioned something about the predictive state representation. This also uh, wasn't mentioned in the class. You should probably read it from the paper which is linked in the video descriptions. Okay, these are the PSRs. Okay, so these are like typically four methods what people use to solve for MDPs. Okay, so yeah, I think that was all I had to cover for today. It's 7:37. Maybe we wait till 7:40 before closing the session, right? Yeah. So with this, I think we have covered most of the thing or most of the stuff that we wanted to cover up until the week 12 content, because week 11 content, lecture content was very less. So I tried to merge the content of week 11 and week 12 together. And even after doing that, we still have half an hour left, right? We have to close the session early today. So it's a good thing we have covered entire theory part. Next week will be the last live session for this course for this semester. I hope you guys are preparing well for the final exam that is upcoming. I don't know the exact dates. I'll have to check. But I hope your preparation is going right. Uh, Next week, we'll just look at the Python code related implementations. Okay. I can show you certain toolkits that people use for coding, uh, designing the environment and uh, executing or coding different reinforcement learning algorithms. Okay. So that's my plan for next week. If you have any questions, you stay back. I'll be available for a couple of minutes. Otherwise, thank you. Thank you for attending so far. And with this, we can close the session. So I'll wait for 2 minutes. Rajat Agarwal has raised a hand. Yes, you have a question?
I like your session today. It was a good session.
Okay, thank you. Thank you for attending. Okay, guys. I hope you had a good time. Uh, I'll wait for 1 more minute. Okay, since there are no more questions, I think it's a good time to stop for today. I covered whatever needed to be covered till week 12 so far. And yeah, I'll see you next week. Okay. Thank you for joining. Bye. Have a nice weekend. I'll stop the recording.